So, we are looking at minimum cost spanning trees, and we said that there are two broad strategies, and the first one of them is called Prim's algorithm, right. So, in Prim's algorithm, we will try to find a minimum cost spanning tree by incrementally growing it from a small edge. So, in particular, we could start with the smallest edge, right, and then we will extend the tree by adding the smallest edge from the tree. So, we already have a tree in Prim's algorithm. So, starting with one edge, so one edge is a tree, right. So, we will start with something that is already a tree, and we will see in what way we can grow this graph within the graph that we are looking at, what way we can extend this tree while keeping it a tree in a minimal way, right. So, we want to add the smallest edge to the existing tree to get a larger tree until we can grow no more. So, that is broadly Prim's algorithm, right. So, here is Prim's algorithm at work. So, I first start with the smallest edge. In this case, the smallest edge weight is 6. So, I start with the edge 1, 3. Now, I have to grow this tree, right. So, I can either add this edge, or I can add this edge, or I can add this edge, or I can add this edge, because I cannot add edge 8, because if I add the edge 8, then I would have essentially, if I add the edge 8, then I will have two disconnected components. I would have 2, 4 and 1, 3, right. So, I cannot add the edge 8. So, I have to add among the others the smallest edge to extend the tree. So, for instance, I would pick the edge 10, because 10 is the smallest of these trees. So, now I have this. Now, among those which are connected, the smallest is 18. But if I add 18, I will end up creating a cycle. So, this adding 18 will not allow me to keep this a tree. So, the smallest edge I can add which keeps it a tree is, so I cannot add that edge. So, the smallest edge I can add to keep it a tree is 20, right. And finally, now I have reached the point where I can add the edge 8. So, I can add that, and now I get this spanning tree. So, this is Prim's algorithm. We start with the smallest edge 6, take the smallest edge which is connected to the current tree 10, smallest edge is connected but does not form a cycle, that is 20, and then 8, and then I get a spanning tree, right. So, we have to argue that this is correct, of course, but this is Prim's algorithm. Right. So, Prim's algorithm says incrementally build a spanning tree. So, we have a set of vertices which are already in the tree. We have a set of edges which are already in the tree, right. So, the set TE forms a tree over the set TV, both of which are parts of the existing graph. So, initially I have nothing, right. So, one strategy that we saw now is to start with the minimum cost edge. So, we start with the smallest cost edge I comma j and make that our initial set of tree vertices I comma j, and our initial edge is this E, right. And now I will choose the smallest edge which starts in the tree and ends outside the tree. So, U is in the tree, V is outside the tree, and I will add this edge, and I will add the corresponding vertex V to the set of tree vertices. So, I will add UV to the U comma V edge to TE, and I will add the vertex V to TV. So, just to run it by hand. So, initially here TV is empty and TE is empty. Then we pick that 1 comma 3 edge. So, we say that the set of tree vertices is 1 and 3, and the edge 1 comma 3 is there. Now, I pick 1 comma 0 or 0 comma 1. So, I add the vertex 0 to my tree vertices, and I add the edge 1 comma 0 to my tree edges. Next thing to add is 1 comma 2. So, I will add the vertex 2 to my set of vertices and the edge 1 comma 2 to my tree. And finally, I will add the vertex 4 and the edge 2 comma 4, right. So, this is the representation of Prim's algorithm as we go along. So, let us see why this is correct, right. So, the correctness of this algorithm is based on what is called the minimum separator lemma. So, supposing I can take any set of vertices, right, and partition it into two parts, right. So, I have U and I have W. And now, let me look at any edge which crosses the partition, right. So, U is on, so this is small u and W, right. So, small u is on the left hand side, small w is on the right hand side. Then the claim is that no matter how I construct a spanning tree on, so this is part of the entire graph. So, no matter how I construct the spanning tree on this entire graph, it must include this red edge, right. So, that is what the minimum separator lemma says. So let's assume for simplicity that all the edges have different weights. So all edge weights are distinct, right? So this is the picture now. So my entire set of vertices, so this whole thing is my entire set B, right? So this is capital V. This is my set of vertices, and it is split into two parts, right? One part capital U and one part W, and I have an edge of going from capital U to capital W of minimum weight. So I might have many different edges here, right? And among these, this is the smallest one. So the claim is that this must be part of every minimum cost spanning tree, right? So supposing we have a tree which does not include this edge, right? So the tree that does not include this edge, because it is a spanning tree, connects the entire graph, right? So in particular in this tree I have this path, right? So I have a path from U to W in this tree, right? So the blue dashed lines represents a path from U to W. So this path P starts in capital U, right? So this is the path from U to W, right? So this path starts on the left hand side in the red set and it ends on the right hand side in the purple set. So it must cross at some point, right? It has to go from here to there. So this must be some edge which takes it from capital U to capital W, right? So let this be the first such edge. Okay. So what do we know? We know that this is the smallest edge which crosses, and here is another edge which crosses, and we have assumed that all the weights are distinct. So we know that the weight of E is strictly less than the weight of F, right? So what we can do now is remove F and construct the path the other way. Right? So we get something which excludes F and includes E. So it will certainly have less cost because we have taken a bigger edge and we have dropped it to a smaller edge, and now you have to argue that this is a spanning tree, right? So that's easy to check because you now just have to check that everything is still connected. So anything that was connected through F, right, is now connected through E, because if I can go from here to here, and so supposing let me assume that I had some other path which followed this thing, right? So now I can instead go from here to here, go all the way around, come here and then go there, right? So every path which was there before through F can now be rerouted via E, and in particular because E is smaller than F, the new tree that I have constructed is strictly smaller. So this minimum separator lemma is very powerful. It says that if I take every way of partitioning my thing, then the smallest edge connecting these two partitions must be there in every particular tree. Right? So what if two edges have the same weight? Well, then we will kind of break ties by assigning some index, and we will say that one edge is smaller than another edge either if it has a lesser weight or it has a smaller index, right? And then in that sense we will say that the smallest edge must always be there. So what we have in Prim's algorithm, remember, is that at every point we have constructed the tree so far, right? This is TV with a set of edges, and then we have the remaining part of the graph, right? And what we are doing is we are trying to find the smallest edge E such that U belongs to TV and V belongs to the rest, right? So the smallest edge which takes me from the tree outside the tree. But this is like saying that I have a partition, right, and I am looking for an edge which goes from this partition to that partition, right? And therefore from the separator lemma, it says that this edge that I have picked in Prim's algorithm must be part of every spanning tree, so it's always making a correct choice, right? So actually we started with the smallest edge, right, and the smallest edge must be there in every spanning tree, because if ij is the minimum edge, in the graph, right, if I take my partition as I and V minus I, right, then clearly since I to j is the smallest edge anywhere in the graph, this must be the smallest edge connecting I to the rest. So it has to be there. So that's for starting with the smallest edge is a safe thing to do. But if you look at this minimum separator lemma, it actually tells you something a little bit more general than that, right? It says that for any vertex if you take, so it's not necessary, in this case we are looking at that particular minimum edge I comma j and saying I and the rest or j and the rest must be connected by this edge. But if I take any vertex v and I take the rest of the vertices, right, then this vertex, because the original graph is assumed to be connected, this vertex must be connected to the other vertices somehow, right. So if I take the smallest edge coming out of this vertex, it goes to the other set, right. So I am sitting here in V and here I have V minus V, right. So here I have a bunch of edges, because it's connected I have at least one. So if I take the minimum among these, it's going to be the smallest edge connecting the partition small v to the partition V minus V, right. So therefore the smallest weight edge leaving any vertex has to be part of every MCST. So instead of starting with this minimum cost edge, we can actually start with any vertex and just start with a trivial tree consisting of one point. And then say, okay, from this one point I want to grow this tree, so I want to pick the smallest edge which leaves this tree, this one point. And then I get one edge which may not be the overall smallest edge, but it will be the smallest edge from this V, but still we will get a correct answer, because that will be still by the minimum separator lemma part of every spanning tree. Okay. So here is an implementation, right. So we are going to keep track of the tree that we have built, okay, and we are going to keep track of the distance of every vertex, because remember that we have to take the shortest distance for every vertex from the tree that we have built and pick the vertex which is at the shortest distance, and we are going to keep track of the tree edges. So remember, so this is basically going to tell us what we call TV, right, and this is going to tell us what we call TE. And this is distance V is going to tell us the distance from every vertex to TV, that is the smallest edge connecting V to the tree, and we are going to pick the minimum among those at every step, right. So these are the three things that we are going to keep track of. So initially, as usual, we define infinity, so we are directly working with a list, because we know that it cannot be worse than working with a matrix. So we work with a list, right. So we initialize visited to be a dictionary, distance to be a dictionary, and tree edges to be a list, right, to empty dictionary, empty list. Now the first thing what we do is that for every vertex we initialize visited to false and we initialize distance to infinity, right. So initially there is no tree, so every vertex is unvisited and every vertex is infinitely far from the tree because there is no vertex in the tree, right. Now we set some vertex to be in the tree. So we said before that it is not necessary to start with the minimum vertex. So we can just pick vertex 0 and say start the tree at 0, right. So eventually in the tree 0 has to be there, and we said that the smallest edge connected to 0 will actually form part of the tree. So once we have thrown 0 into the tree, then 0 is part of TV. So if I have 0 there, right, vertex 0, and if I look at all its neighbors, they are now connected to the tree by edges to 0, and that now defines their minimum distance to the tree, right. So for every vertex in the adjacency list of 0, I set the distance to that vertex to be the distance of that edge, the weight of that edge, right. So if I have u 0 to v with distance d, it will be a pair v comma d in the adjacency list of 0. So I will set the distance of v to be d. So this is my initialization. So I have set up a trivial tree with one vertex, and I have initialized the distance of all its neighbors to be the distance of the edge from 0 to its neighbor, right. And now I do the usual thing, which is I will try to calculate the minimum distance, right. So I initialize to, I will do the traditional minimum distance thing. I will set minimum distance to be infinity, and then I will find it, right. And I will set the next vertex that I want to add to be none, right. So essentially I will go through all the vertices, right, and I will check whether it is visited, and if its minimum distance, right, is currently smaller than the minimum distance of the, so this is, right. So basically I take an edge u comma v, I check that u is visited, v is not visited, and this is the distance, right, and I check whether this distance is actually smaller than the minimum distance that I am trying to calculate, and if so, I update it. So, at the end of this loop, I have found the distance which is minimum, and I have found the next vertex, and I found the next edge also, which is the UV. This is the next edge to be added, right. So, if I have not found a vertex to add, I come out of it. So, this will be a paradox, this will be a pathological case when the graph is not connected, which we need not worry about, but I put it for completeness. But in general, I will come to this point, right, where we have now identified this minimum vertex, right. So, we have identified this minimum vertex, and now we set it to be true. We append the edge that we have discovered from u to v. So, there is a bracket there, u to v to be there, right. And now, for every neighbor of the vertex that we have just discovered, for every v comma d which is in the list of next v, if it is not visited, we update its distance, right. So, this is how Prim's algorithm works. But if you look at the complexity of this algorithm, okay, the initialization takes order n, the loop runs n times as usual. Okay. And now, in this loop, we have this which is actually looking at all the edges, right. So, it is saying for every edge, if the starting point is inside and the ending point is outside, then consider the distance and add it, right. So, this is terrible because this thing is actually n times n, right, which could be n cubed, and we would hope that this would be no worse than n squared, right, similar to say Dijkstra's algorithm. So, we have to do something a little more clever to get this algorithm to actually come down to a reasonable complexity. So, we will do the same thing, but we will maintain our information a little differently, right. So, as before, we will keep this visited and this distance, but remember that every time we update the distance, we have a reason to update it, right. So, we updated the distance because we discovered the distance from the most recently added vertex was smaller than the distance we had before, and therefore, this edge represents the edge which connects this unvisited vertex to the tree in the smallest way, right. So, supposing I had this thing and I had a vertex v there, and now I grow my tree to this point, and now I discover that this distance is smaller than whatever distance I had from here to here. So, I throw away that and I say that this is my new distance, but I also know that this edge is the reason why this vertex has this distance, right. So, when I compute the minimum distance, I will also recognize which edge I added. So, I will keep track of this neighbor, right. So, distance v tells me how far away v is from the tree, but neighbor v tells me which vertex in the tree is actually connected at that distance. So, remember that this is not the shortest path distance, this is a direct distance, this is an edge connecting v to the tree, right. So, where is the other endpoint of the edge? That is at neighbor of v. So, now this becomes my new thing. I no longer need the tree edges because I will discover them from the neighbors. Eventually, the neighbors will form the tree, right. So, what I will do is instead of keeping the tree edges, I will keep the neighbor, right, and initially the neighbor is also a dictionary which is empty. Now, I initialize visited to false as before, distance to infinity as before, and the neighbor of every vertex I initialize to -1. -1, it should be a name of a vertex between 0 and n minus 1. So, since it is -1, it is not defined, right. Now, as before, I start by setting visited of 0 to be true, and now I do two things. For every neighbor of 0, I set its distance to be d and I set its neighbor to be 0. So, now when I connect 0 to all its neighbors, right, I make them all point back saying the reason my distance is d is because my neighbor is 0. So, now that I have this list of neighbors, I am in a little better shape. I can do what we did in Dijkstra's algorithm, which is among now all the vertices which are not visited, I find the distance, and among these I find which ones are I find the minimum distance and then I find the vertices correspond. So, this is exactly the same code that was there in Dijkstra's algorithm. We first find the minimum distance among the unvisited vertices, and among those we find out which vertex actually has that distance. So, we get a candidate to add, right. So, we get this candidate next v and we make it true, but we do not need to know how it was connected because it was already connected by its neighbor. So, that is the critical thing. So, we do not need to know which edge to add because that edge is implicitly there in neighbor of next v, right. And now we go through all the neighbors of this newly added node, and when we update the distance, we also update the neighbor. So if the distance reduces because of next v, then the neighbor becomes next v. So in this way, as we update the distance, we also keep track of this witness, as it was, saying why did my distance come down to d? Because it came down through this vertex u. So when I pick up this vertex to add to my tree, I already know which edge I add. I add the edge from my neighbor to myself. Right? So if I return the set of neighbors at the end, then from the neighborhood relation, I know exactly I can reconstruct the tree. It will tell me the neighbor of 3 is 2, it means that the edge 2, 3 is in the tree, and so on. Right? So this is an alternative way of implementing the same idea of Prim's algorithm, except that instead of keeping the tree edges, we keep track of this neighbor for every unvisited vertex, saying this is my current best way of joining the tree. Right? So in this case, we scan all the non-tree edges, and after we do all this, then the complexity improves because the scan to find the next vertex is now order n. Right? Earlier it was order m. So this is very similar to Dijkstra's algorithm. In fact, so Prim's algorithm and Dijkstra's algorithm are really more or less the same except for this update operation. Right? In one case, you update the distance to be the distance to the burnt vertex plus the new edge. Here we just construct the distance from the burnt vertex, don't plus it. You just take the distance from the most recently burnt vertex to the tree, to this vertex. So we want to know the distance to the tree and not the distance to the source. Right? That's the only difference. So Prim's algorithm is really a kind of variant in some sense of Dijkstra's algorithm. So like Dijkstra's algorithm, though it remains order n squared for adjacency lists, we will see that if we can do this more cleverly of finding the minimum in a collection, then we can do better. Okay. So Prim's algorithm is our first algorithm to build a minimum cost spanning tree. So it starts with an arbitrary vertex or the minimum edge, as the case may be, right, and it grows this tree by adding to this existing tree the smallest edge that can be added. So we had this very powerful minimum separator lemma, which showed that every edge that Prim's algorithm adds to the tree is necessary for the tree to grow. Right? So it basically justifies why this strategy of, again, it's a greedy strategy like Dijkstra's algorithm, where I look around the tree and I find the smallest edge which is connected out of the tree and I add that to the tree. Right? So I am not going to look further down and see whether I can take the second minimum now and maybe later on it might help me. Right? So every time we have a greedy strategy, we have to justify that this choice which is frozen now is going to work in the future. Right? So just like in Dijkstra's algorithm, we had that argument telling us that later on we cannot find a shorter path. Here it says that every such greedy choice we make is guaranteed to be correct because it must form a part of every minimum cost spanning tree. Right? So the implementation is also very similar to Dijkstra's algorithm, and like in Dijkstra's algorithm, the complexity is n squared even with adjacency lists, but the bottleneck is really this thing of among the unvisited vertices find the minimum. Right? So this is a common problem that arises in a lot of things, that I have a collection of objects and I want to find the minimum and remove it, or I want to find the maximum and remove it. They are kind of symmetric questions. So we will look at a data structure for this later on, which will allow us also to reduce the complexity of Dijkstra and Prim's algorithm to something from n squared down to something more like n log n.